So welcome. Thanks very much for presenting your gene-environment interactions with essential heterogeneity. We'll turn it over and ask questions throughout. Thanks very much.
All right, I'll make it full screen. I hope you can see the screen now.
Yes.
First of all, thank you very much for inviting me, Jason. Thank you everyone for being here this morning. Maybe a little bit about myself. My name is Johannes. I'm a PhD student at RWI Essen, which is an economic research institute in Essen, Germany. I do mostly education economics, health economics, and for about 1.5 years, I've been into the GBI literature as well. Today, I'm presenting joint work with my lovely co-authors, Fabian Dehos, who's a freshly appointed assistant professor at Constructor University in Bremen, Germany, Hendrik Schmitz, who's a professor of economics and statistics in Paderborn, Germany, and Matthias Westphal, who is a professor of economics in Hagen, Germany. Maybe a little bit about how this paper developed. We started out being interested in sort of cognitive decline, cognitive performance over the life cycle. And as economists, we were mostly interested in how sort of the choices you take lead to, well, your cognitive performance later in life. Then it evolved into us being interested in the genetic component of that. And as we got more and more into literature, we started being interested in many more outcomes and many more sort of choice gene interactions. And it culminated in what you'll hear today, which is us trying to somehow marry the gene environment literature with the sort of Heckman world of heterogeneous treatment effects and selection in a treatment. I'll just go start with the presentation now. As all of you are probably aware, is that the gene environment interaction literature is growing, and at its core is estimating the interaction between genetic components and environmental factors in producing outcomes. You can sort of think about this in a very simple regression equation like this, where an outcome Y is subject to genetic components G, environmental components E, and their interaction. The central parameter of the literature is really beta 3, which is the interaction coefficient. And intuitively, as you would interpret it, if it has the same sign as beta 2, you would probably conclude that genes and environment reinforce each other in their effect on Y. If it has the opposite sign, you could argue that the environment has the potential to offset differences due to genetics. That is a generalization. I realize that, and it kind of depends on how your Y is defined, how your G and E are defined. But in general, I think it's fair to say. Most problematic is that environment is always endogenous. As economists, we're interested in causal inference, and endogeneity is the central problem that we're trying to overcome. Environment is endogenous. So what people do is you would usually take an instrument, most often a natural experiment, to then instrument your E and G by E. The problem that we're showing is when you're doing that, when you're instrumenting E and G by E, you're doing that usually with two-stage least squares estimation. What that does, or what that can do, is it can yield you an inconsistent estimate of your central parameter beta 3 that may even have the wrong sign, and that would then lead you to make wrong conclusions from your estimates. In the paper, we describe the problem, we propose a solution, and we're doing that using a simulation example, and then we apply this to real-world data. The real-world relationship, we're estimating it, we're trying to show it on, is the effect of education and its interaction with a education polygenic score on diabetes later in life. Let me start very basically with our basic setting. At the moment, we're using data from ELSA. It's the English Longitudinal Study of Aging. Our outcome is, like I've told you, binary variable for currently having type 2 diabetes. In our sample, about 11.3% of individuals have that. So that's quite a lot actually, but you have to remember that it's a study of aging, so most people are quite old, certainly a lot older than you would find in the overall population. Our environment E is education. It is coded as having left school at age 15 or later. And in fact, 75% of people in our sample have done that. Our instrument we're using to instrument the environment is a compulsory schooling reform in the UK that increased school leaving age from 14 to 15. So if you were born before April 1933, you would have the opportunity to leave at age 14 or even earlier. And after that, so if you were born from April 1933 or later, you would have to go to school until the age of 15. And G, our genetic component, we're using an education polygenic score. We're using a binary version of that, even though it's nicely distributed, as you're probably aware. We're using the 75th percentile to split. So if you're above the 75th percentile of this education polygenic score, you would be considered high polygenic score. If you're below that, you would be considered low polygenic score. A bit about our sample, we're using all waves from ELSA. It's waves 1 to 9 from 2009 to 2002 to 2019. We're using plus or minus 7 cohorts around this pivotal cohort of 1933. That doesn't really matter too much. It's just a preferred option. Unfortunately, and even though I have wrote them many emails, we don't have information on month of birth of the ELSA participants. So we need to drop the pivotal cohort of 1933 because we cannot assign them to either being born before the reform or after the reform. The final sample is about 2,660 individuals. With repeated observations, we have about 16.8K observations. And like I've mentioned, most of them are quite old. The majority is between 70 and 80. A little bit more about education reforms in the UK. There's 2 big ones that have been used extensively in the literature. We're using the first one, the left one. It's the 1947 reform that increased school leaving age from 14 to 15. You can see that I've highlighted the cohorts. The cohort for this reform is the 1933 cohort, and before that, basically 60% of students left school at age 14 or even before. And after the reform, it slowly went down to basically 0. A little bit about how education and diabetes are related. As you may be aware, type 2 diabetes, which we're looking at, typically develops later in life. Its biggest risk factors, other than your family history, your heritage, and your age, are obesity and a sedentary lifestyle. That being said, literature has found that individuals with lower socioeconomic status are at a higher risk of developing type 2 diabetes, and education may be able to act as a protective factor against type 2 diabetes. Now, the channels through which this could happen could be through obesity, health knowledge and behavior, income, or occupational choice. Basically means that when you're more educated, you're less likely to be obese. You're more likely to exhibit healthier behaviors or have more knowledge about healthy behaviors. You tend to have more income, so maybe able to afford a gym membership, something like that, or you may be able to get into healthier occupations. I want you to take these channels with a grain of salt because at the moment, there's not too much in the literature about these channels. So just as a word of caution. I want to move on to something more interesting, which is education diabetes in a G/E setting. The way we see it is that there are 2 interesting angles one could follow. First one would be to estimate an interaction between education and the genetic risk for diabetes. Sort of the classical thing where you choose the polygenic score according to your outcome. And what this does for you, it could potentially tell you about how diabetes develops and how education could maybe be used to offset some of the genetic risk associated with diabetes type 2. We're not doing that. We're going the second route because we're interested in sort of people's choices, people's educational choices, and how that relates to genetic predisposition. So what we're doing is we're estimating an interaction between education and genetic predisposition for education, so an education polygenic score. And what this tells us about is educational choice, as I've mentioned, its genetic component, and how people respond differently to educational reforms based on their genetic endowment. The way we do that is, like I've mentioned, using two-stage least squares, because educational choice is endogenous. We're using the educational reform. What you can see here is both stages of the two-stage least squares regression. Equation 1 is the first stage where our educational parameter is explained by the instrument, so being born in 1933 or later, the genetic component having high polygenic score or not, and the interaction term. The residuals of E and G by E are then plugged into the second stage to induce a random variation in E and G by E and estimate the effect on Y, our outcome, diabetes. We do not have many control variables. They're not necessary, but we felt, not strictly necessary, but we felt that it would be good to include gender and first 10 principal components of the genetic data, which is sort of, I guess, a convention in literature now. And we also have this F of T. These are cohort trends, squared cohort trends, and their interactions with the instrument. This basically makes it equivalent to estimating a full fuzzy regression discontinuity model. Our main assumptions for an RDD are that individuals just to the left and just to the right of the cutoff, so people born before 1933 and people born after 1933, are comparable. This is just another way of putting the continuity assumption of RD. And if this assumption holds, we obtain local average treatment effects for E and G by E for compliers. Let me show you the first stage. It looks like this. As you've already seen, the educational reform had a big impact on the universe of students in the UK. You can also see that here. On the x-axis, you have the running variable. This is the relative distance to the birth cohort of 1933. And on the y-axis, you have the treatment or the environment. In this case, it's our education dummy. And before the reform, you can see that basically 40% of people stayed in school until the age of 15 or later. And after the reform, it was above 90%. So we have a very strong instrument, and the share of compliers to the schooling reform is about 55% or even higher. Now let me show you the reduced form. On the x-axis, you again have the running variable, but on the y-axis now you have our outcome, the share with type 2 diabetes. This is just raw data, but still you can see a jump at the cutoff and also changing dynamics, so changing slope of the regression to the left and to the right. I don't want to stress this too much. I want to move on to our regression results. What you can see here is the OLS results of the second stage and the two-stage least squares results of the second stage. And the way you would interpret these is that an additional year of education for those with low polygenic score would lead to a 5.4 percentage point reduction in the probability to have type 2 diabetes. So this is this regression coefficient. And then the G by E coefficient is, in the two-stage least squares case at least, is minus 0.02. So you would conclude that the additional effect for the people with high polygenic score is another 2 percentage point reduction. So you would end up with a reduction of 7.4 percentage points for those with high genetic propensity. And this would then, according to what I've shown you in the beginning, lead us to conclude that education and genetic propensity seem to reinforce each other, because the E and G by E coefficients have a sign that goes in the same direction. Now, as you probably can see, we're lacking statistical significance here. We're interpreting the sign of the effect, the size of the effect, but we're not able to estimate the effects very precisely. This is not the main problem, however. And in order to show you what the problem with these results actually is, we need to take a step back and look at the potential outcome model that underlies microeconometrics, and look at how the local average treatment effect is actually computed by two-stage least squares. We begin with a very, very simple potential outcome model where we have two potential outcomes, Y1 and Y0. Y1 is the potential outcome with more education. Y0 is the potential outcome that is realized without more education. You can put that in an observation rule, which is just a switching equation where you plug in E equal to 1 or E equal to 0, and you will basically end up with the corresponding potential outcome. Now, the big problem is that you can only, for each individual, you can only observe one of these, because you're either leaving school at age 15 or later, or leaving school at 14 or earlier. And classic two-stage least squares computes the local average treatment effect, in this case, as the expected value of Y1 minus Y0 for compliers. We do have three different groups in our sample. First, the compliers. This is the individuals who take on the additional year of education because of the instrument, so because of the reform. You have always takers who always take on more education regardless of the instrument status, and never takers who never take on more education regardless of the instrument status. Now you can visualize these three groups like this on a continuous X scale that is somehow a scale of the aversion to taking the treatment. On the very left, you have always takers with a very low aversion towards the treatment. You have on the right never takers with a high aversion to the treatment, and somewhere in between you have compliers. What you can then do is you can visualize these potential outcomes like this. For always takers, you can only observe Y1 because no always taker will not take the treatment. For never takers, you can only observe Y0s because no never taker will take the treatment. But for compliers, you can observe both of these potential outcomes, or you cannot observe both of these potential outcomes, but you can calculate the difference between them as the local average treatment effects with two-stage least squares. The problem is we don't only have the simple case, we want to estimate an interaction. That's why we also need to include a second dimension apart from E, which is the G dimension, the genetic dimension. So now we not only have two potential outcomes, we have four. Y11 is the potential outcome with more education, so with E equal to 1. And high genetic endowment, so polygenic score equal to 1. And Y10, more education, low genetic endowment, and so on. The observation rule then gets a bit more complicated and looks a bit more daunting, but it works just the same. You plug in each permutation of E and G. So you plug in E equal to 1, G equal to 1, E equal to 1, G equal to 0, E equal to 0, G equal to 1, or both equal to 0, and you will end up with the corresponding potential outcomes. Now what you can do is you can rearrange this so it looks a bit more nice. What you have here is you have all the E's, all the G's, and all the G times E's. And this awfully resembles our regression equation, the simple regression equation we've looked at in the beginning. Now, what you can see here is that our central parameter, beta 3, so the interaction coefficient, corresponds to this difference here. This difference can be broken down into the difference between gains with G equal to 1 versus gains with G equal to 0. Now we need to understand how this translates into the real world. We're doing this using a simulation example. This is the setup. We basically simulate all 4 potential outcomes. The parameterization doesn't really matter, but we've set it up in a way so that it shows the properties we want to show. You have the highest potential outcome with more education and high polygenic score, lower outcome with high education, low polygenic score, and so on. E is endogenous to the model. It means that it is subject to G and to Z. And an individual in our simulation would choose E equal to 1 if the gains of choosing E equal to 1 are greater than the cost of choosing E equal to 1. The costs are simulated or are equivalent to these error terms here we have. And the benefits of choosing E are basically simulated by the first stage regression, which is this, where E is subject to G and Z. Our instrument Z and our polygenic score G are Bernoulli distributed with probability 0.5. That means basically they are randomized into 0 and 1. And the error terms are standard normally distributed. What this setup allows us to do is, other than in the real world, we're able to just calculate the true interaction effect using the equation I've shown you before. It is 1.5. The true interaction effect between of G and E is 1.5. In our example, you can verify that by simply subtracting 0.5, 0.3, and 0 from 2.3. Now, the interesting part is when you use two-stage least squares, because we've set up everything. We have an instrument, we have E, we have G, we have Y. If you use two-stage least squares to estimate the interaction effect, you will end up with minus 1.3. So minus 1.3 is not plus 1.5. So what's happening here? For that to become clear, we have to look at what two-stage least squares actually does, how two-stage least squares computes the interaction effect. And this is basically how you have these two differences in potential outcomes. Those are defined for compliers that are, for a group of compliers that is compliers when G is equal to 1, minus the expected value of this difference for a group that is compliers when G is equal to 0. Now you will notice here that we have two groups of compliers. In our setup, these are two distinct groups of compliers. So you can either have G equal to 1 or G equal to 0. And this basically complicates things because if these groups do not overlap, so if the group of compliers that is only complier if their G is equal to 1 and the group of complier that is only complier if their G is equal to 0 do not overlap, which is very likely, and they have different values of these potential outcomes, your two-stage least squares estimates will differ from the computation, or from the real computation I've shown you. And we can visualize this again. This time we have 4 groups. At the very left with the x-axis basically stayed the same. It is still the unobserved resistance to the treatment. At the very left with the lowest resistance to the treatment are the always takers. These are always takers regardless of their G status. At the very right, you have the never takers with the highest resistance to taking the treatment, who are never takers regardless of their G. And in the middle, you now have these two complier groups. You will notice that the first group is only complier if they are at G equal to 0. Second group is only complier if they are G equal to 1. Now you can visualize your means of the potential outcomes again. And the way you would now compute the local average treatment effect of the gene-environment interaction would be like this. You would do it in each of these two complier groups by comparing the blue and the red circles. So basically subtracting. The problem is two-stage least squares compares these two, the filled out circles. And as you can see, the red filled out circle is above the blue filled out circle. And if you subtract red from blue, you will end up with a negative estimate. Now, what's wrong with two-stage least squares? I would say nothing, but if two things hold, you may get into these problems. First thing is having multiple complier groups. In our case, multiple complier groups happen if G, so your genetic component, affects the instrument complier status. And the second is effect heterogeneity with respect to compliers. What this means is basically having this gradient of potential outcomes here, with the always takers having the highest payoffs, never takers having the lowest payoffs, and compliers having payoffs in between, but still different payoffs. So if these two hold, your two-stage least squares estimate will mix up different effects of environment by genetic endowment, which is basically the interaction that we're interested in, with multiple complier groups that have different potential outcomes, which we want to control for. But two-stage least squares cannot control for. It is pretty simple to see when this problem does not occur. The first instance would be if there's only one complier group. As you can see here, one complier group equals no problems. You can simply estimate the gene environment interaction effect like this. This may happen if, for example, your genetic variable does not affect your instrument status, or your instrument take-up, sorry. Second scenario when the problem does not occur is if you have homogeneous treatment effects or no selection into gains. Selection into gains is just a way of saying that there is a gradient, so that always takers have higher payoffs, never takers have lower payoffs, and you have this gradient in the potential outcomes. If you don't have it, like here, and you have a flat gradient basically, two-stage least squares still compares the wrong circles, but it doesn't matter because it turns out to be 1.5 in the end again. Now, let's say we have the problem. What can we do about it? I have simply drawn a line through all of my points here to visualize what we can do about it. Namely is to prevent these horizontal comparisons and only allow for comparisons that occur vertically. And if you compare at any of these points on the x-axis vertically, these two lines, you will always end up with the gene-environment interaction effect of 1.5. And how we can do that is by estimating marginal treatment effects. Marginal treatment effects are treatment effects that are evaluated at each point of distaste for taking the treatment. And that has been our x-axis all along. Only that we have had groups here with different distaste for taking the treatment. And now we can extend this to a continuum where at the very left, you have very low resistance or very low distaste for taking on education. And on the right end, you have very high distaste for taking on the treatment, and the payoffs at the left are higher than on the right. And what you would then do is you would estimate these marginal treatment effect curves. They will not always look as nice as here. And you would then simply compare vertically these two lines and basically be able to calculate at any point of distaste the right gene-environment interaction effect. I want to bring this back to our setting. How likely is it in our setting that these two problems I've shown you are actually occurring. And I would say it is very likely because we're likely to have multiple complier groups because individuals with higher genetic propensity for education, remember we're using an education polygenic score, are less likely to be compliers and more likely to be always takers. So if you have a high genetic propensity for education, you're more likely to have more years of education, and you are more likely to have chosen to stay in school until the age of 15 or even later anyway. And that's so that is an indicator for our G, so the genetic component affecting instrument take-up, and that would then lead to multiple complier groups. And second thing is we have different potential outcomes along the distaste for education because individuals tend to select into education according to unobserved gains. That is a property that has been described a bit in the literature and that we can also show. It is basically responsible for the gradient in these potential outcomes and then the gradient in our marginal treatment effects as well. So what we did is we basically estimated marginal treatment effect curves for our example. They don't look as nice as the visualization I've shown you. We've also chosen to estimate linear marginal treatment effects instead of non-linear ones because they're just less demanding because we already have power issues. What you can see here, or what we needed to do, is we would need to estimate the marginal treatment effect curves for G equal to 1 and one for G equal to 0. And then evaluate them at their midpoint to calculate the local average treatment effects of the gene-environment interaction. And the way you would calculate local average treatment effects on using marginal treatment effects is as a weighted average of marginal treatment effects. And as the weights, you would sort of use the density of the compliers along your UE, which is the distaste for taking on education. And with linear marginal treatment effects, this turns out to be the midpoints. So that also makes it easier. You just take the midpoints of each of these lines and then calculate vertically the differences between these lines. And that will give you the true gene-environment interaction effects. What you can see here is the wrong comparison that the two-stage least squares makes. You can also estimate it using two-stage least squares weighting. And it's just, I don't know, I hope you can see that. You would compare these two circles again, and that would lead you to the wrong gene-environment interaction coefficient. What you would actually want to do is at each of these points, compare the green and the red lines, and you would end up with two different gene-environment interaction effects for each type of G. Now I have that here. I have a summary of our gene-environment coefficients we've estimated throughout the journey. In the first line, you can see, again, the interaction estimates from two-stage least squares I've shown you in the beginning. It was minus 0.02. In the second line, you can see the same thing estimated by marginal treatment effects with the two-stage least squares weighting. That was basically this wrong comparison I've shown you here. In a perfect world with lots of data, lots of individuals in the data set, they would be equal. Here they're not because we have power problems, but at least they go into the same direction. So both of these wrong comparisons have estimates with negative sign. And interestingly, at the bottom, you can see the marginal treatment effects of the gene-environment interaction coefficients with proper weights for each of these genetic types, and they're positive. So what two-stage least squares would lead us to believe is that education and genetic propensity for education reinforce each other in their effect on type 2 diabetes. But what estimating marginal treatment effects and eliciting the true interaction effect would now lead us to believe is that the benefit of the additional year of education is actually lower for those with higher genetic propensity. And that would lead us to make the opposite conclusion that education would be able to offset the effect or would benefit those with lower genetic propensity for education. But again, like I've mentioned, standard errors are a big issue. We're just not able to estimate the effects very precisely. I'm already at the conclusion, but I still have some drawbacks, and maybe we're able to discuss further drawbacks at the end. So like I've hopefully shown you, the estimates of an interaction term using two-stage least squares may not have the intended interpretation you want from an interaction term. Applying this to G by E means that estimating the coefficient can generate a bias of large size and unclear direction. And as you may have thought about already, this is not limited to G by E settings. So actually, every interaction you estimate using two-stage least squares can be subject to this problem. The thing is that usually interactions are estimated or interaction effects usually are in table 5 of the paper or are reported in the appendix and are just not that prominent. But in the G by E literature, the interaction effect is actually the core parameter. And so we feel like this literature or these types of settings are perfect of showing the relevance of these properties. And we've shown that marginal treatment effects or estimating marginal treatment effects can help you recover true interaction effects. Our empirical results, like I've shown you, are first of all that you would lead, or two-stage least squares would lead you to believe that advantageous genetic endowment for education would boost the education effect on type 2 diabetes. But actually, marginal treatment effects, estimating the true interaction effect would lead you to believe the opposite, so that education would serve those with lower genetic propensity for education. At the moment, our study is far from perfect. We have still a lot of problems. The biggest one I've alluded to a couple of times is that our sample size is just too small. And we have a demanding estimation strategy, meaning two-stage least squares leading to local estimates and marginal treatment effects being even more local. And that requires usually a lot of observations that we just simply do not have at the moment to estimate precise effects. Second one is that we have a binary instrument. If you have followed the marginal treatment effects literature in any way, you will probably have heard the notion that it is not possible to estimate marginal treatment effects with a binary instrument. That is in fact not true. It is possible to do that. It just severely restricts or the flexibility of your MCEs, basically. And I think the literature is catching up on that now. It's still a problem. We would like to have nice continuous instrument to really show differences in the distaste for taking the treatment and then be able to estimate nice marginal treatment effects in a nonlinear way. We simply don't have that. The second one is one of the criticisms we've gotten the most is that we're actually using binary G with an arbitrary cutoff, and it's totally fair. I mean, we have very nice polygenic score that has nice distribution, nice normal distribution across the population, and we're basically cutting it at the 75th percentile, and that doesn't make any sense. And I tend to agree. We're doing it because it's just easier to interpret the coefficients, just easier to work with, and it works well with our sample and our explanation of these 4 groups. Otherwise, you would have many more different groups with many more potential outcomes to worry about. A little bit about what we're planning to do about it. We're currently applying for the UKB, which probably most of you are familiar with, in the hopes of increasing our effective sample size. So the local sample size we're actually using to estimate the effects by a factor of, I would say 5 to 10x. And actually yesterday we got the approval from the UKB. So we're hopeful that actually we can start working with the data soon and move away from ELSA because we just have sample size problems. Second one is we show how to estimate marginal treatment effects with a binary instrument. And we're working on even another method to do that. That is hopefully even more convincing. It is still another thing to worry about and another thing to sell the readers. Because we really, usually what we would want a clean solution, and estimating marginal treatment effects is a clean solution, but it cannot, doesn't really apply to every setting, I would say. But we're working on a bounding exercise where you not point identify these marginal treatment effects, but bound them from the upper and lower bounds to hopefully informative ranges. And the third thing we're doing is we're using more of the variation in the polygenic score. For example, deciles, which are arguably a more robust concept than just splitting it. But maybe we can even use more variation. And I've brought one of our, as a last slide maybe, one of our most recent results. This, what you can see here is the shares of compliers, always takers, and never takers to our compulsory schooling reform across the deciles of the education polygenic score. And what you can see is that with lower polygenic score, lower education polygenic score, people are more likely to be compliers to the education reform and less likely to be always takers, and that basically shifts as you go towards the right, so towards higher education polygenic score. What this tells you is that, first of all, there is large type heterogeneity within the polygenic score, and that our polygenic score certainly affects how individuals react to the education reform. And we're trying to develop this more because what we want to do is we want to be able to really say something about how the genetic component that we're using affects or interacts with the choices, educational choices people make in shaping these outcomes. And it could be a cool thing to kind of develop this further out and just to show different heterogeneities within the polygenic score and reaction of people to reforms. With that being said, I want to close and say thank you very much for listening. If you have any questions, please feel free. If you have any comments, any criticisms, you can please feel free to ask. Please feel free to write me an email. Thank you very much.
Thanks very much. So we'll have people, and had to leave. We're in a shared room, so I think we're going to be just lining up ourselves, Johannes. One thing, just when you were talking about which PGS to select, could you go into some more detail maybe about why, like what research question selecting the education polygenic score allowed you to examine? Maybe say it again. Instead of, as you already said, the more typical answer would have been select the diabetes polygenic score.
Right. I mean, we are really interested in learning about occupational choice, so not educational choices, and how genetics is related to this. This also comes back to what I've shown you in the what I've just shown you. So that's basically how differently people react according to their genetic endowment to the education reform. And this would be the motivation for us to choose the education polygenic score instead of the diabetes polygenic score. That being said, the diabetes polygenic score, as I've mentioned, also has some interesting questions that are certainly relevant, I would say. The thing is that it's not, I'm not sure, I haven't tried it, but I would imagine that it's not as suitable to show the properties we want to show, namely that when you're estimating the interaction effect with two-stage least squares versus marginal treatment effects, you get different signs of the effect. So you really, what you need is the heterogeneity, and you need so effect heterogeneity, and you need multiple complier groups. And with education polygenic score, we have this, and we're also confident that we're that we can contribute something interesting.
Yeah, so I would maybe summarize that by saying you're in some sense a lot more interested in the first stage than in the second stage, which is it's not much clear why diabetes is a good candidate for the outcome as compared to really anything else like wages. You said occupational choice.
Yep.
Do you share that view that diabetes maybe is under conceptualized here as a really interesting target outcome?
No, you're absolutely right. Yes, we are certainly more interested in the first stage, and just because of the properties of the first stage. And like you've mentioned, there is not as much literature about the effect of education on diabetes. So I think we could even contribute there.
But
Does
that
it answer your
literature
question?
I mean, the literature that would be interested in the effects of education on diabetes would probably be less interested in your first stage and all the, the reasons why people are making this first stage choice, essentially, right? Or do you see some kind of parameter that you're getting from that first stage being a good way of pinning down some kind of mechanism or why education might affect diabetes in the long term?
In this setup, we're estimating the interesting heterogeneity is what Heckman and colleagues call the essential heterogeneity. So the basically different types of individuals, so compliers having different treatment effects. So it's treatment effect heterogeneity. And that tells us something about economic behavior, so choice behavior into education. But you're absolutely right that people who probably care about the effect of education on diabetes, care more about the outcome than how the educational choice works. That is true, I would say, yeah. And it's fair to say.
Yeah, just still trying to understand this, but let's say you actually have an ideal polygenic score for compliance, and this is a score that doesn't actually change average treatment effect, right? So then if you throw this score into two-stage least square, my intuition is you would see a positive interaction because, having a higher score makes you more compliant in general. But would you call this artifact, or is it in some way still exactly what people try to estimate in real world applications?
That is an excellent question. It is, I think what you're trying to get at is us needing to figure out whether the problem we've identified is basically happening randomly, or is an artifact, as you said, or is something that is happening systematically. But you're absolutely right. If, like I've shown, where is it? Here. If we don't have multiple complier groups, for example, and that can happen in, I'd say, many different scenarios with many different polygenic scores and many different environments and outcomes, you don't have this problem. So it's you will not have the problem with two-stage least squares every single time. You will only have the problem with two-stage least squares if our two prerequisites are met. And this is not going to be the case in every setting. And I would even go as far as saying that if we were to have taken the diabetes polygenic score, we would probably not have different complier groups, because it's hard to imagine diabetes polygenic score affecting educational choice or affecting people taking up the instrument.
I guess just to follow up, I guess I am willing to accept these conditions you showed us, but I wonder why you call the inflated estimate bias instead of exactly what we want to estimate. Because the idea is, if you have some kind of treatment and you apply it to a population, and if genetics determine how likely an individual is going to comply, it's going to be a complier. Is it what you call complier? But anyway, then in a way, this actually, all I'm saying is, in my mind, this actually does amplify the education effect if genetics modify complier behavior, right? So I just wonder, why do you not want to estimate that? In a way, it is a causal effect difference between treated and untreated group, right?
You're absolutely right. It is the correct causal effect. My point is, and I probably should have phrased it better, that it is about the interpretation of what you're estimating, right? Usually with gene environment interactions, you would make one of these interpretations. But if our two conditions are met and two-stage least squares actually identifies something different, then you would not be able to make these interpretations anymore, because even though two-stage least squares still identifies our causal effect, it compares to the wrong points. Because what you want to calculate when you are estimating two-stage least squares is actually this difference here, that allows you to make these interpretations. But if two-stage least squares, which is estimating this, does not correspond to the equation that you would use to calculate the interaction effect traditionally, you could, these are two different things. And I guess you're right, it's totally fine for us to estimate two-stage least squares. It's just about the interpretation of the estimate that may not be retained. And I should have probably worded that better.
This is kind of what Q is at. I think this is kind of what Q's asking. It's a little bit more of a just conceptual what if point. If there was a PGS for what you're calling distaste for education, and you label it U sometimes, how would that, like, what would you do with a measure like that?
I mean, a polygenic score for distaste of it for education would just be the negative of the education polygenic score, wouldn't it?
Well, that's an extreme version. I mean, that's an extreme interpretation of the polygenic score, isn't it? To say that all it is
possibly, yeah,
is taste for education.
Possibly, those are two very different things. Distaste for education is just the wording that comes from the marginal treatment effects. This is, by the way, unobserved distaste. So it is
what I'm suggesting, what I'm saying is that, let's say that from some other data, there has been a GWAS on distaste for education, and therefore you could port that over to ELSA, and you could try, and therefore you have a measure that's related to this unobserved distaste for education. Okay. Is there some way that you would bring that into your analysis?
I guess you could then directly estimate these marginal treatment effect curves. Usually they are rooted in a Roy model, where you would estimate these unobserved distaste for education. And if you were to observe it directly, which I don't think it's possible, you could possibly directly estimate the response. I'm not sure. I don't even know how you would calculate such a polygenic score, because you would need an outcome, right?
No, that's right. This was more of a kind of a silly question, because you're thinking of the polygenic score for something related to complier status. So one minor point there. Your last slide had the estimated never taker part, and was it curious to you how little that changes across the PGS distribution?
Right. I would say, first of all, the problem with a compulsory schooling reform is that in theory, there should not be never takers, right? If you have a schooling reform that forces students to attend until they're 15, there shouldn't be any never takers. There shouldn't be any people who could say, well, I'm born after 1933, but still I'm going to leave school at 13. That shouldn't happen. So it is probably measurement error. And also then related to us having power problems. What I would say about the share of never takers not changing is that polygenic score, how I understand it, would mostly affect always taker and complier status, because basically never takers cannot be moved to choose education regardless of the instrument. So why would I don't really see a scenario why that would change. It would be more about the complier status changing. But you've identified another potential problem that we have, which is the never taker share that we should not have.
Maybe just a very quick follow-up. Still, this is me thinking out loud, trying to understand this. So let's say this is a clinical trial, right? And you have a pill that can treat diabetes, but it tastes really bad. So then some people would just refuse to take the pill, even in a clinical trial. But there's a genetic score that basically determines how bitter the pill would feel, right, in your mouth. Right? I think that's basically kind of the setup you have here, right? So then I guess in a clinical trial, this compliance factor would bias the estimation of treatment effect, I guess. But if this is some kind of a policy intervention trial, I'm just wondering philosophically, do you care? Because there in the clinical trial case, you actually want to estimate whether or not you take the pill, what's the difference does it make? But if you want to decide, well, if we if I have some kind of a law that decides all the kids have to stay in school for 1 year, what kind of public health implication it would have? In some way, this compliance is embedded in the parameter you try to estimate, right? Just why do you want to take away this compliance factor from the estimation problem, I guess?
Well, I don't want to take it away. If you're just interested in the cause of the effect, so the cause of the law change on some public health outcome, for example, you're absolutely right. You wouldn't care too much about who's the compliers and what is their payoff. If you're just looking at it from a policy perspective, if it works, it works. If it doesn't work, it doesn't work. But if you're interested in the effect of the cause, so if it works, where does it come from? You're interested now in different heterogeneities. So you're then interested in which people are the people that are actually affected by it. And does the intervention target the people that it should target? And does the intervention target people who can actually benefit from it? And what you would be able to see here is, or what you generally have with compulsory schooling reforms, is that they target the lower end of the educational spectrum, right? people who leave school at age 14 or even earlier, it's incredibly early. And you sort of elongate that for and make them stay a year longer. That's certainly the lower end of the educational spectrum. And what you would be able to see from this picture, for example, is that these people, or maybe not this picture, but what you would be able to say when you, for example, looking at marginal treatment effects, you would be able to see that the people who benefit the most from the reform are the ones who would otherwise, without the reform, not have taken on more education. So in a sense, the reform is even more salient because it actually targets the people you want to target, namely the people who would not have taken on more education. So that's why you care. I hope it answers your question.
So in the clinical trial example, if you actually do have a polygenic score that predicts how bad the drug tastes, do you want to see an interaction effect or do you want to see a null effect in an ideal analytical setting?
Oh, if you're just interested, again, in determining if it works, you want to see null effect, actually. Yeah.
That's the part I guess I'm not following. Because then I have some kind of a drug that is now available in the market, but your genetic score make you react negatively to the drug, which makes you less likely to take the drug, right? Then in that interaction analysis with the genetic score to predict bitterness of the treatment, I correctly sort of inferred that, right? But why would you not want to see that in this education setting, I guess?
Oh, you mean why we would? I mean, I don't want to see anything. I am pretty much agnostic. We're just trying to describe what we're seeing.
But I think you called one version of this as a bias, and you sort of propose a different way to estimate this correct parameter, right? I'm just trying to understand philosophically which one of these actually is what we want to see in an application like this. And I'm not an economist, that's why I get confused by the big picture stuff here. That's why I wanted to follow up on this.
Maybe we have to take a step back. All I'm trying to say is that if our two prerequisites hold, then what you're estimating with two-stage least squares may not have the same interpretation as the thing as what you want it to be. That's all I'm saying. But you actually want to have this interpretation of the interaction effect as a classical interaction effect in the econometric sense, because you want to be able to make statements like genetics and education reinforce each other, or education is maybe able to offset genetic risks. And in order to consistently make these interpretations, you may have to use marginal treatment effects to estimate instead of two-stage least squares. That's all we're saying. And we're just illustrating it with the example, which, as you've mentioned, is maybe not the right example to do it, maybe not the best example to do it, but for now, it works in showing that, I believe.
Can I ask you a question?
You have to speak up. Your
right.
speaker's right there.
So based on your research, what are some surprising significant implications for public health policies or economics model?
Can you hear all that?
Sorry.
No,
sorry.
Maybe if you're willing to speculate on implications for public health or something like that, we're giving you license here to go beyond your data, maybe like your one exercise, maybe. Can you say about, from a health or public health perspective, if you were trying to sell this approach and these results, what you would tell them about why or if they should be interested?
At the core, this is about econometrics. So you would probably not, as an econometrician, care too much about these implications. If I were to speculate here, what we're or the core of what we're trying to do is we're trying to see how genetics interacts with choices people make. We're trying to understand educational choices people make depending on genetic predisposition, for example. In terms of implications, it would always have to involve you maybe knowing your polygenic score for education at age 2, or your parents knowing that. I'm not sure if we want that. So maybe if you get your genome sequenced and then you someone calculates your polygenic score for education, your parents are more likely to, knowing that you have maybe a high propensity for taking on education, your parents will maybe more likely to put you on another school track, depending on the school system you're in. Again, I'm not sure if we actually want that. So I guess there might not be too salient of policy implications in there. I'm sorry.
No, that's fine. This was a speculative implication question. Thanks very much for this great talk. I think as you already said, we'll be very interested in what you find in the UK Biobank. We could really see an expansive. We could see you doing many outcomes and seeing if the results differ and being hopefully quite well powered with that a much larger data set. So maybe you'll check back with us to see how that's going.
Oh, absolutely. That would be great. I mean, are you guys working with the UK Biobank a lot? I mean, we don't have a project yet. It's our first project with the UK Biobank. We're very excited to try. We're hoping for good things.
We're using UK Biobank and more recently, all of us, 2 very large cohort data sets or very large data sets of from different countries, as you know. But that was going to be my first point, which you preempted, which is why aren't you doing this with the UK Biobank when you have, essentially using the Patrick Turley, Sylvia Barcelos type PNAS paper,
yep.
and saying, yeah, exactly, and saying doing more or less what you're talking about doing. So I guess that's going to be upcoming.
That's the plan. Yeah. Yep.
Well, thanks very much for joining us. Have a great day and weekend.
Thank you so much. Thank you so much for your comments. Again, if you have more questions, more comments, more criticisms, feel free to write me an email.
Perfect. Have a nice weekend.